Welcome to the fourth of 14 videos on the arc flash truth no one explains. My name is Joe Chacon. I'm the president of Podge LLC and Chacon Engineering. I'm a licensed professional engineer in multiple states and have been an electrical engineer for almost 30 years. Please like and subscribe as this helps us get this important information in front of more people. This video is going to introduce you to calculating arc flash incident energy. We'll focus on the preparation stage mostly in this video. The standard I will be referencing is IEEE Standard 1584 2018 edition. Also reference IEEE Standard 1584.1 2022 edition. I don't see why IEEE made 1584, which is called IEEE Guide for Performing Arc Flash Hazard Calculations, and then made 1584.1, which is called IEEE Guide for the Specification of Scope and Deliverable Requirements for an Arc Flash Hazard Calculation Study in accordance with IEEE Standard 1584. Seems like they could have just put everything together, in my opinion. I'll start at the 30,000 foot level and work down. That means we need to address the assumptions first. First, you have single line drawings. Very important. Can't do them without them. 2, you know the modes of operation for the equipment. 3, you have a short circuit study for the various modes of operation. 4, you have a time current coordination study for the short circuit study. 5, you know the equipment has been properly installed, operated, and maintained. 6, you're a licensed engineer in the state for the study. 7, you know the actual working distances. 8, you know the bus gaps and enclosure sizes. That's a lot. That's why I insist on visiting a site when I do an arc flash study. IEEE 1584.1 2022 provides a checklist to help further break down these assumptions. There are over 40 items in that checklist. Also note that the IEEE standard explicitly only focuses on calculations for three-phase AC systems between 208 volts and 15,000 volts or 15 kilovolts. It gives some guidance on other configurations. So that means engineering judgment is needed for those other configurations. I'll address that in future videos. The standard is also limited on fault currents tested, gaps tested, working distance, and enclosure sizes tested. Now that you've gathered all this information, you can make your model and move on to calculating bolted fault current. These videos are not about how to calculate bolted fault current. That could easily be 10 videos just by itself. So I defer you to books like these. I will give you a rough estimate that gets you close by looking at a transformer nameplate. Look for the impedance, kVA, and voltage. In this example, 5.5%, 2500 kVA, and 480 volts. 2500 kVA divided by 3, divided by 480, divided by the square root of 3 is 3007 amps. 3007 amps is then divided by the impedance of 5.5%, results in 54,673 amps of bolted fault current. That is a crude way to calculate bolted fault current. The next video will look at the effects of bus gap and enclosure size. You'll see that they can greatly and significantly affect incident energy.